Yeah, with calculus it always helps to have the answers, for sure. Nothing yet, but 4 pages might take a little bit longer than normal.
Yep.
Is there any that you can verbalize and we could kind of get started? Yeah, hold on. I just saw it come in. I just saw it come in. Which one do we want to start with?
We can go with number 2. Because I already did number 1 in class.
It looks like these are 4, 5, 6, and 7. Looks like 5. You want to start with 4? Let's see, hold on. No, 6, 5, 6, 7, and 8.
Is there a 1, 2, 3, 4? Oh, there you go.
Well, maybe there's problems. Just the document itself was. Okay. Where do you want to start? At 1?
2. I already did number 1.
Okay.
First. I'm thinking it's just C.
Yeah, exactly. In other words, that's the definition almost of integral as net change.
Yep.
We're going to integrate the function over the first 3 hours. Notice that this looks a lot like that, but it's not the same at all.
Yeah.
Okay. Area between the graph and the x-axis from 1 to 3. How would I set that up as an integral?
The integral from 1 to 3 of 3x squared plus 2x dx.
Okay. Go ahead and integrate that.
I should take the antiderivative. X cubed squared.
Just to apply the power rule, it's real simple. You add 1 to the exponent and divide by the new exponent. So this becomes 3x cubed divided by 3 plus 2x squared divided by 2, which is x cubed plus x squared. We're going to evaluate that whole thing from 1 to 3. You know how to do? Yeah.
Plug in 3 first.
Okay. So that would be 27 plus 9.
Plus
so
9.
36. What?
Plus 2.
Minus.
Oh, minus 2.
Always want to subtract the evaluation at the lower level, so the answer should be 34.
Yep.
Okay.
That cut off. Number 4 says from -2 to +2.
Okay. Which of the following expressions gives the length of the graph? So they're talking arc length.
Length of the graph.
So let's review our arc length formula.
Isn't it 1 plus dy dx squared, the square root of all that?
Well, it's either dy dx or dx dy, depending on what your function is. So it's 1 plus either dx dy squared dy, or it's 1 plus dy dx squared dx. Which one do we want to use here?
Dx dy.
Yeah, they've given us a function of y. So I can take dx dy easier than I can take dy dx. I can do it either way, but there is a problem here. Let's examine this a little bit more. If we look at the function, this function can be written x equal y cubed, or y equal what?
The cube root of x.
X to the 1/3. So the cube root of, or y equals the cube root of x is that. There's a problem with integrating that.
Goes through 0.
Well, it's not differentiable throughout its domain. It's not just that it goes through 0, there is a vertical slope right there. So we can't integrate the whole thing if we integrate it using this function. We run into a problem right there, and your calculator is going to run into a problem right there also. It's not going to like that. However, if we treat it as x equal y cubed, that doesn't have a vertical tangent. So that's what we want to use, is x equal y cubed. I'm not, something wrong with that graph. Let me think about that for a second. This problem's in the book even. Hold on a second. I'm tempted to say, where's arc length? That's chapter 7, isn't it? Yeah.
I think I figured it out. All I did was just take the derivative with respect. I just did dx dy, and then I did, so I got 3y squared, and then I just plugged that in and I squared it, and then I got c, and that's the answer.
Good. That's what I was going to do. The only thing that bothers me is that function. I'm not sure that that doesn't have a vertical tangent to it. I got to think about that for a little bit, but I know that that's going to work. We're going from -2 to 2 of square root of 1 plus 3y squared, which becomes 9y to the 4th dy. So that should work, and yeah, I still have x equal y cubed. That is the answer?
Yeah.
You have the answers, so you know, huh?
I think I might have sent them to you. Just, it doesn't show you how to work it out, though.
No, that's okay. That's huge in calculus, having the answers. A lot of times you can figure out how to work out a problem if you know the answer. You got to be a little careful that you don't rely on that as too much of a crutch, because it's very easy to rely on it as a crutch. One thing that gives you a clue that that's the correct answer is the fact that we're integrating from y equals minus 2 to plus 2, which means it has to be an integral of dy. And since it's a dy for sure, then for sure this has to be dx dy squared. And we're going to pretty much ignore the fact that there might be a vertical tangent there. I'd have to look that up. Next time we have a session, I'll have a little more information on that. Because it seems to me that we still have a vertical tangent between minus 2 and 2. In other words, if you actually go to figure that out, your calculator might give you a problem doing that integral. I'm not positive about that. I'm going to play with that in between our sessions and see whether there really is a vertical tangent there. Seems to me that there is. Maybe not. Which of the following definite integrals gives the length of the graph y equal to e to the, what is that? E to the x?
E to the e, yep.
E to the x between x equals 0 and x equals 1. Okay, we have a function of x. We're going from 0 to 1, so it's going to have a dx in it, as all these do. So all we have to do is figure out what dy dx is and square it. Y equals e to the x. How do we get dy dx? This is kind of an unusual solution. Whenever your exponent, or excuse me, whenever the x variable is in the exponent, you can't differentiate it right away. In other words, if I said y is equal to 2 to the x, dy dx is not equal to x times 2 to the x minus 1. You cannot use the power rule when x is in the exponent. So it becomes a little more difficult to differentiate. Well, the way we differentiate this is by taking the log of both sides. Natural log. Okay? So if I take the natural log of that side and the natural log of that side, now I can write this right side a little bit differently, and I can also implicitly differentiate. You remember implicit differentiation?
A little bit.
Okay, well, with implicit differentiation, let's talk about implicit differentiation. If I give you this, and I say implicitly differentiate it, you don't have to solve it for y and explicitly differentiate it. You can just immediately go in and differentiate it. If I want dy dx, then I start there. That's 2x plus 2y, but that's different than x, so I have to follow it with a dy dx. In fact, if I come across a variable that is not x, I have to follow it with dy or d of that variable dx. In other words, if this was r squared plus y squared equals 2, and I want dy dx, well, it's 2r dr dx plus 2y dy dx. So the basic rule of implicit differentiation is if you come across a variable different than the denominator, you have to follow it with a d of that variable over dx. All right? Okay, so let's differentiate this implicitly. What's the derivative of natural log of y?
1 over y.
dy dx. Because y is different than x. Okay? What can we do with this expression to make it becomes e to... Yeah, we can bring the e to the x down because it's an exponent, so we can put it in front based on our rules for logs.
And isn't the natural log of e 1?
It is. So now, what does dy dx equal to?
Is equal y e to the x.
And what did the problem want? Okay. We want the arc length. So this is dy dx. So we're going to integrate 1 plus dy dx squared. So that's y squared. What's e to the x squared?
E to the 2x.
Good. dx. This was going from what to what? From 0 to 1? So this is what we're looking for as an answer. We have that anywhere? Well, they got something close.
Where we plug in e to the x.
Right. In other words, we know what y is, right? So if we want, in other words, we really don't know how to integrate that because we have a y and we're trying to integrate it with respect to x. So you can only integrate it with respect to x if your function is entirely in x. So we have to go back and substitute for y. And we know what y is. Y was equal
e to the x.
to the e to the x. So now we have from 0 to 1, square root of 1 plus y squared. If I square that, same base, different exponents, I'm going to add the exponents. E to the 2 e to the x is this times another e to the 2x. I think that answer might be on there.
It is, but it looks like they pulled out a 2.
Well, they've combined it. In other words, now we're multiplying e to the 2 e to the x times e to the 2x, so I can add the exponents and remove the second e. So this is an answer that we should find on there. E to the 2ex.
Looks like they pulled out the 2.
You're right, they did, and it's this answer right here. It's A. Yeah, by just factoring out the 2. You get this. Nice problem. But it does illustrate this process of having to take the natural log of both sides before you can differentiate it. It's only after I take the natural log of both sides that it allows me to get the x variable down onto the line. As long as it's in the exponent, I can't differentiate it. But once it's on the the line in front of the natural log of e, I can differentiate. Even if the natural log of e was not equal to 1, I could still handle it. I could use the product rule if I had to.
Uh-huh.
Okay, let's see. Number 6. Okay. Base of a solid is the line x plus 2y equals 4. Well, if I want to graph that line, I'll find the x and y intercepts. The x-intercepts when I let y equals 0. So the x-intercepts at 4. The y-intercept is when x is 0, so the y-intercept's at 2. Connect that. There's the line.
Mm-hmm.
And the coordinate axes. What is the volume of the solid if every cross-section perpendicular to the x-axis is a semicircle? So you have a cross-section like that, and then another cross-section, and so forth and so on.
Mm-hmm.
They said it's perpendicular to the x-axis, so it's not oriented the other way around.
Mm-hmm.
Okay, well, we need to find the area. Notice that the skinny side of these semicircles is dx. The skinny side is always your differential that you're going to integrate. So I'm going to integrate the area of the semicircle dx from where to where?
0 to 4.
What is the radius of this very first semicircle?
2.
The diameter is actually 2.
Oh, so 1.
So 1. But more importantly, it's not 1, it's f of x evaluated. So the area of that semicircle is pi r squared, right?
Mm-hmm.
Divided by 2, actually, because it's a semicircle. So I'm going to sum up all of these, and r is f of x divided by 2, correct?
Yeah.
So in place of r, let's write f of x divided by 2. So now this is what we have to solve. Well, what is f of x?
Wait, why did you divide it by 2? The second time?
Because the radius is the function value divided by 2. It's not the function value. In other words, if I want to know what the radius is right there, I'm going to take my f of x value, divide it by 2 to give me the radius of that semicircle, divide it by 2 again because it is a semicircle instead of a circle.
Okay.
So f of x is what? We need to figure out what f of x is. Well, that's the same as y, so let's solve this equation for y. Y is equal to 4 minus x divided by 2, correct? That's f of x. So I'm going to substitute that for f of x. So we have 4 minus x divided by 2. That's f of x, or that's r, the radius. Excuse me, that is f of x. we still have to divide it by 2. So let's make this 4. There we go. That's what we're looking to do, is right there. Do you know how to evaluate that integral?
Would we just square it, or would we have to? Not exactly sure.
Okay, let's... First of all, we can take out any constants, right?
Mm-hmm. Pi over 4.
Yeah, so let's take out the pi over 4, leaving from 0 to 4, and we have, we have 2 minus x over 2 quantity squared dx, right?
Mm-hmm.
How do we do that?
Foil it.
Yep. So this is 4 minus 2 of this times that, which is 2x,
Mm-hmm.
plus this squared, which is x squared over 4 dx. Now we have the integral of the sum of 3 things, which is equal to the sum of the integrals.
Mm-hmm.
So this is 0 to 4 of 4 dx. This is the integral of 2x dx from 0 to 4. And we're adding the integral of x squared over 4 from 0 to 4 dx.
Mm-hmm.
What's the integral of 4?
Would be 4x.
Minus the integral of 2x
X squared.
plus, what's that integral?
It'd be 3/4 x cubed.
Remember, add 1 to the exponent and divide by the new exponent. So I have to divide this by 3, which means I'm dividing by 12. In other words, I add 1 and divide by 3 times 4. It's already being divided by 4. So, and then I have to evaluate this thing from 0 to 4. The 0 part's going to be real easy. That's going to be 0. So all I have to do is evaluate it at 4. And then multiply it by pi over 4. So we have 16 minus 16 plus 64 over 12.
So it'd be times by pi over 4.
So now we have 64 pi over 48, which is what? 8, that's 8 over 6 pi, that's 4/3 pi, B. Is B the right answer?
I will check. 6, it says A.
2/3 pi?
Yeah.
Well, looks like I made a mistake with one of my 2's somewhere. I'd have to go back and review all my math.
Oh, it says she has pi over 2, not pi over 4.
Ah, that's why she got an answer half of the size. Okay. How did I get pi over 4? Let's see. Oh, because I was dividing by the radius and the semicircle. And this 2 up here accounts for, no, that's right. Let's think about this for a second.
This is what she said. She says the diameter of the circle is 2 minus 1/2 x. The radius is 1 minus 1/4 x. So she said the area is pi times 1 minus 1/4 x squared divided by 2.
She said the diameter was 2 minus x over 2, right?
Yeah.
What else did she say? So
The
the
radius
radius
is 1 minus 1 over 4x.
1 over x over 4.
Mm-hmm.
Oh, which is, so this is the radius.
So then she said the area is pi times the radius squared divided by 2.
Yeah, it's pi times the radius squared, all divided by 2. So that's how she got the pi over 2 outside the integral. And then she just integrates that. Okay, so I would have gotten 2 pi over 3 also, instead of 8 pi or 4 pi over 3.
Mm-hmm.
Yeah, I made a mistake by multiplying. I halved it one too many times.
Mm-hmm.
I mean, you have to have it because the radius is half the diameter, and you have to have it again because it's semicircles. So that's always a little tricky. You always make sure you have to have it twice. If I did it 3 times, it's so tricky. All right, so we're just doing a half hour tonight, right?
Yep.
Okay, well, that's a good place to stop where we left off at 6. So our next session, we're just going to finish these problems?
I don't, tomorrow I think I'll have a new one because I have to finish this one tonight.
Okay.
Because this is homework for tomorrow, and then, I'll probably have a new one for the weekend.
Okay.
And Monday as well.
Sounds good. Sounds like you're doing better with this calculus. It sounds like you know a whole lot more tonight than you did last time I talked to you.
Uh-huh.
Is your grade improving a little?
I did do a retake test, and I did do a little bit better, so that brought me up, but I just had a quiz that I didn't do so good on.
Okay.
But I think I'm understanding it more. It's just, I don't know.
Yeah,
whenever I take quizzes and stuff.
It feels like you are understanding it more, to me, by a lot. I'm rather amazed at how much more you seem to be understanding it than the last time. It might just be the questions, too. These are more standard. Yeah. These are standard kind of calculus questions. Whereas last time, you really had some of the esoteric questions that they love to ask at Chatfield. And that you're lucky those kind of questions probably won't be on the AP Calc exam. The AP
Like
Calc,
those harder ones?
No, they're easier. I would say the AP Calc exam is going to have questions more like tonight.
Oh, really?
Yes, rather than like what we had last time.
What about in college? Like, what's the difficulty? Because I'm going to have to take calculus in college. What's going to be that? What's that going to be, like, difficulty-wise?
You're not going to believe this, but your high school is probably going to be your hardest calculus you take. Unless you major in math, or even if you major in engineering.
I will be.
Calc BC. You're a senior?
Yep.
So you won't be taking Calc BC until you get to college. Well,
no.
I've tutored a lot of calculus in college, and I've always been amazed at how much harder my high school calculus students' course is.
Really? So they train us way well.
Seriously. It's always amazed me. I've got sophomores at DU majoring in engineering whose calculus, when I tutor them, is less tough than my calculus BC student that I have right now. I got 2 of them.
Mm-hmm.
Both of them are tougher than the DU sophomore engineering calculus program.
Oh, jeez.
Yeah, it's pretty amazing. So, if you can get through Chatfield's calculus courses, you're doing pretty good. You'll be
Yeah.
well prepared for college. Although you'll have to take the equivalent of BC, and that's tough. That's tough in itself because it gets into infinite series and stuff, which is really a hard part of calculus. But anyway, I'll talk to you at our next session.
All right. Thank you.
Okay, Matthew. Do people call you Matt or Matthew?
Matthew.
Matthew. Okay. Talk to you then.
All right. Bye.